and start sharing my screen. All right. All right. Good morning, everyone, again. Today, I'm going to finish ray tracing shading slides. Actually, we've already finished, but we've just went quickly over the reflection part. So I'm going to go over the reflection part in detail, which is the recursive part of ray tracing. And then I'm going to start, in order to go synchronous with section 1, I'm going to start talking about data structures in computer graphics. Although, I mean, I had in my records that texture mapping would come next, but I mean, switching texture mapping in ray tracing and data structures is not a big deal. So I'm going to also go with the same set of slides as section 1, and we will talk about data structures in computer graphics today in the 2 hours, and I plan to finish all of them. And also, I want to clarify certain things about the assignment. When we talk about reflection, it will be clear, I guess. But if you have any questions about the assignment, we will also talk about that. You may ask them anytime you want using the chat box or unmuting yourself. All right, so if you remember, this is we talked about shadows. So in the shadow, so first of all, the first part was we applied the basic illumination model for a point we see in our ray, and we computed the ambient and diffuse and specular component of that illumination model, and we added to our point's color. So everything is additive, all right? So this is really important. With the ambient color is added by default, regardless of whether we are in shadow or not. And for every light source, so this is what we have here. As you can see, before we go over every light source, the pixel color is initialized to the ambient color. Okay, so this ambient color, the ambient component, actually is the ambient color's intensity multiplied by the ambient reflectance coefficient of the surface. And as in the assignment 2, the materials will have different reflectance coefficients for different component of that color that is accumulating. So for ambient, the object may act like it's a red object. If its reflectance coefficients are 100, we are going to multiply 100 with the ambient light source intensity. It may be a gray light. In that case, only the red component will have a non-zero component, a non-zero value added to the pixel color. So depending on, so here again we multiply, so this all LA, LD, and LS multiplies the intensity of the light source with the corresponding reflectance coefficient of the object. So as you can see, regardless of the light sources, initially the pixel color is assigned to the ambient component. And then for each light, we go over every light source one by one in the scene, and we check whether there is any object that prevents this light source, from this point light source, this ray hitting the point that we see. So in other words, is there any other object in between the point light source and the point X that we are currently seeing? All right, if that is the case, then we continue the light loop. If there is, if that is the case, if we are in shadow, we do not add the diffuse and specular component due to this light source. We just skip to the next light source in the queue, in our for loop. So this is the continual light loop. If otherwise, if you're not in shadow, we add the diffuse and specular component to the pixel color. As you can see, everything in pixel color we add values. It's all additive. Now, so this is after we have the shadows. Now, the reflection is just the reflection from other objects is just another. So after we have the shadow and diffuse, specular, and ambient components, the image looks like this. The reflection component, that is light that may reach this point from other objects, is just another light source that is going to be added to ambient, diffuse, and specular additively as a separate component. So you may consider it as the fifth value to be added. For example, the first one is actually, yeah, it's going to be the fourth one. So ambient, diffuse, specular, three of them are added. If this object has some reflectance coefficients, which are, there's also another thing, in ambient reflectance coefficient, diffuse reflectance coefficient, specular reflectance coefficient, we also have another set of three parameters for the same object to see how reflective it is, how mirror-like the object is. And it's another three reflectance coefficients, just like the ambient, diffuse, and specular. It will tell us how much of the light that is coming from another object this point x reflects. Okay, so it's another triplet of values. For example, if it's 0.2, 0.2, 0.2, it means that this surface point x also reflects 20% of whatever reflective light that is coming from another object. So it's going to be, if we are going to compute recursively, first we are going to compute the reflected ray. By the way, you may also argue that if you look at this, if you look at the reflected rays, so this is the picture for recursive ray tracing. So in this part, as you can see, we just consider a single ray that is reflected from here. But for example, in specular, we did not do it like this. In specular, we were considering rays that are in a cone. But that would be very difficult. If imagine, instead of tracing a single ray, if we were to trace all the other rays that could potentially accumulate at this point. This is what happens in real life actually, but this is really difficult to do because even tracing a single ray is very time consuming because we are going to be recursively tracing it in a couple of more times. If we were to consider rays, all the rays in a cone, it would be extremely difficult. So this is what the second bullet is about. This is extremely costly to look at all the possible reflected rays from this point. So we will do this reflection only for perfect mirrors. Saying that, we are only going to consider as this fourth component, the reflective component, we are only going to consider a single ray that is reflected from this primary ray with respect to the normal on the surface. Okay, so this is what we will be doing in this recursive part of the ray tracing. And whatever color we compute for this reflected ray, we are going to, this color will be considered as a new light source, point light source that is shining light to us at this direction. And we will just multiply it with whatever the reflective. I'm just going to open the door. The cat wants to go out. Sorry about that. Okay. When they're outside, the door is locked. They want to go in and they want to go out when they're inside. So we should not have any closed doors at home. Anyway, sorry about this. So as I said, whatever color of ray we compute for this reflected ray recursively, we will just treat this as if it's our primary ray, and we are going to compute the color of this as if there was an image window at this very spot at X, and the ray is going in this direction. But what is missing in this recursive ray tracing, you may have noticed, is that there is no image window, there is no image plane d distance away from this reflected ray, right? So even if the object is very close to us, we would be able to see that reflected ray. So the difference of these reflected rays from the primary rays is that we do not generate multiple rays here. There is only a single ray. That is the computed reflection of this primary ray with respect to this normal of the surface. Since there is the single ray, there are no multiple pixels. There is just a single ray, so there is no image plane in front of this with d distance away. These things are although it's recursive, there are some differences with respect to the primary ray. So these reflected rays, there is only just a single ray that we follow. There is no image plane in front of it. There is no distance d. So we will just treat this, for example, even if there is an object here very close, we would be able to see that. So if the intersection occurs, if this reflected ray intersects with an object at t is less than 1, we would be able to see the reflection too, right? There is no since there is no image window in front of this reflected ray, however close another object is, we should be able to see its reflection on this point. So the threshold we used for t, which was t should be greater than 1 because it has to, we can only see objects that are in front of the image window. It doesn't apply to these reflected rays. Because the reflection part, there is no image window that is certain distance away from us. So we should be able to see objects that are very close. So I think there was some. Is there a question? So in the assignment, I think it wasn't very clear. I mean, this t greater than 1 threshold was confusing for some of the scenes. So Bilgin informed us that some students had some questions about this t is greater than 1 threshold. So in the homework, actually, I think to make your life easier, even for the primary rays, this t is greater than 1 threshold was not applied. So even if there was an object closer to the eye than the image plane, it was visible in the example output. So this t is greater, instead of using t is greater than 1 threshold for the primary ray, the threshold was just t is greater than 0. So I think Bilgin is going to send a clarification about this, but this is not so much important. So let me also try to draw it here on GIMP, what I'm trying to say. Okay, so let me scale this up a little bit and move it. Okay, so what I mean is this. Flatten the image and then, yeah. So we have actually an image window here, which is not shown in this figure, right? We are sending our rays to centers of pixels through this image window or viewing window. All right. So here in, for example, in forward rendering pipeline in OpenGL, this plane in which the viewing window lies in is also sometimes called a near plane. Okay, near plane. So in OpenGL, for example, if there's an object that is closer to you than the near plane, then that object is not visible. Or you can only see objects between the near plane and the far plane. There is also a far plane in OpenGL. We are going to see that. So anything between the near plane and the far plane, we will be able to see those. All right. So in order to simulate what we already have in OpenGL, we can actually, in our ray tracing, we can also impose this restriction, saying that we don't want to see objects that are closer to us than the near plane, which is that image window which is d distance away from you. But for ray tracing, this near plane's position is not so crucial. I mean, what you can say is that, okay, why do I have this restriction in ray tracing? I want to see any object that is just in front of the eye and in front of this focal point. Even if there's an object here, I want to see it. You may decide on that, all right? So I think in the assignment, this is how it was given to you. So if when t is greater than 0, if there's an object here, it is still projected on the image plane here, and it is shown. All right, and this should actually be easier to implement, because this makes primary rays the same as reflected rays. There will be no difference in terms of this thresholding, because if the primary rays also are treated as if t is greater than 0, any object with t is greater than 0 is going to be visible, then they become just like the reflected rays. So when you're writing your recursive ray tracer, it becomes easier. You do not need to distinguish between primary rays and reflected rays in that regard. All right, so even if we have the t is greater than 1 threshold, okay, I just mentioned that this t is greater than 1 threshold does not hold for these reflected rays, because for the reflected rays, there is no image plane in front of them. The reflected ray, even if there's an object here, it should be visible, all right, because this ray is not generated by with this perspective vision. This ray is generated as a single mirror reflection ray. All right, so I just wanted to clarify this issue. Any questions about this? I hope it's clear. All right. Now, so what I also did not talk in detail last time was this reflected ray. We compute a color for that. Okay, so it will be good to have a function to have that says compute color, which gets a ray as input. Okay, compute color, and it gets a ray as input. Okay, and we are going to intersect this ray with. At this point, this will be just like a recursive function. This compute color that was going to be first. Actually, it can have actually another parameter, which could be the depth, or not the depth, but ray count. We may call it ray count, or the number of recursive calls. Let's call it d. All right. We may have another parameter d here, which we will initially call it with 0. This for our primary ray. This recursive, this input to our compute color function will be 0. The primary ray will be treated as ray 0. And as we call this function recursively, here we are going to increment this d. So the next time I'm calling this recursively here inside itself, the compute color, the reflected ray, let's call it RE, reflected ray, whatever it is, d plus 1. So I'm going to call it with d plus 1. So this is going to be ray 1. This is going to be ray 2. So and it's going to go like this. And at the top of my function, I will have some if statement saying that if the depth is more than some defined threshold given in the input, because we should give a bound to the reflected rays, because potentially the number of reflected rays could be infinite. Imagine you have a ray that is bouncing between two spheres like this. They will bounce off indefinitely to infinity. So we cannot follow the reflected rays all the way until it doesn't hit anything. It may be the case that the reflected ray hits another object, and it hits another object. So this may go indefinitely. So we usually put a bound on how many reflections are we going to trace recursively this reflected ray. For example, if it's 2, this will be ray 1, this will be ray 2. I will be computing the color of ray 2. If this limit is 2, this other reflected ray will not be computed. So I will have a stopping condition. The recursion is going to stop with respect to this ray count, the current reflective ray number, something like that. All right, so this is what we can have to limit this. In any ways, if the reflectance coefficient of objects, I mean, even if you may ask, does making d a large number, for example, if I make this, not this d, but the threshold on d, if I make the threshold on d a very large number like 20, will it going to make my scene look better? It may and it may not, depending on the reflective coefficients of your objects. Imagine the objects are not perfect mirrors. When we have that's a good question. So there's a question, if we have a mirror-like object in front of the camera, Will we see some sort of a camera object in the mirror? Oh, no, no, no. So this camera itself is really virtual. There are no physical geometric object that is for this image plane, the camera itself, the eye point. They're really things that are virtual. They do not have existence in our real virtual world. Okay, they're abstract objects. So the only geometric objects in the scene are these spheres and triangles, which are not part of the camera actually. So we are never intersecting our rays with the image plane. The image plane itself is not considered a real object part of the scene. It's just something abstract, something virtual. Yeah, exactly. If you want to actually see the reflection of the camera here, at this point you can add a geometric object for your camera and you will see the reflection of the camera itself on the mirror-like object in front of the camera. You can do that. That's perfectly possible. Yeah, thank you. All right, so yeah, what I was saying was this, even if this is larger, if the reflectance coefficient, this reflective reflection coefficients of these objects are small, for example, if an object just incorporates 0.2, 20% of whatever reflection is computed, just incorporates 20% of it to this final computed ray. What happens is that as we move, as we follow more and more rays, whatever effect we may have at this larger reflection, it's going to get reduced and reduced and reduced. These reflective coefficients are numbers that are less than 1 most of the time. It's going to be 1.0 only for mirrors. Okay, if you have lots of mirrors in the scene, then it may be reasonable to set this ray count threshold to a large number to see reflections of objects that are far away, and that requires multiple bounces of ray to be seen. But if you don't have mirror-like objects, I mean, if you have, for example, reflection similar to what we have in this figure, look at this. The tabletop is reflecting only a tiny portion of whatever blue light we have. So it's just like it's still like a mirror, but not. It's like reflecting 20% of whatever's coming here. So in that case, when we follow the ray multiple times, its contribution is going to get smaller and smaller and smaller because we will be multiplying with numbers that are smaller than 1, and multiplying them with 20 times, you will get a very, very small contribution. So the contribution of objects that are very far away in terms of ray bounces, there are many ray hops away in terms of the object ray bounces, their contribution will be infinitesimally small, which means that in real life, actually, we don't really need to follow trace the rays more than 3 times, 4 times. So this threshold of 3, 4 is good for efficiency. It's also we don't require more ray bounces to make the scene more realistic. Okay. Yeah, exactly. So another thing, at the fourth reflection, if all the objects have reflection coefficient 0.2, at the fourth reflection, it already becomes just 1% of the computed color. So it's really you will not be able to see the reflection. You will not going to be seeing that. Yeah, thanks, Bugra. So this is really, I mean, that's why we don't need too many ray bounces. It's also good for efficiency because bouncing every one of those rays is like computing the whole color for a ray. You need to do all the things. You need to compute the ambient, diffuse, specular for that new point the ray sees. You need to do the shadow calculations. Look at this. If the object here, so we are going to compute the reflected colors. Let me go to GIMP. So we are going to compute the color of this one. Okay, so compute the color of this point, new point. Let's call this Y. We need to also see whether this Y is in shadow or not. If this Y is in shadow, then the reflected ray that is coming to this point will not be that much. And therefore, all the computations, the shadow computations, also the reflection computations recursively, it's done for this ray as well. So it's going to be really costly. So we don't want to do it more than 2 or 3 times. All right, the final thing I want to mention, by the way, we talked about this 0.2. Again, this reflection coefficient is actually a vector. If it's 0.2, for example, it's going to be given to you like this, 0.2, 0.2, 0.2. So for each color channel, we do this color accumulation and computation separately. Okay, so an object that is like a mirror, it should have all these equal to each other, but we may have some strange object in which this reflection is only at one channel, for example 0.200. If that is the case, and if this reflected light that is coming here is some blue light, even if it's like 00255, okay, if this we compute this reflected light and it becomes 00255, after the reflection it will be 0, because this reflection coefficient just saying that I can reflect only the red component of whatever is coming to me. Green and blue components, I do not reflect that. So you may have reflections in which you reflect differently at different color channels. All right, so this is just after we compute this color, we just treat it as a light source and we multiply it with the reflection coefficient of this point, and then add it to the other colors. Everything is additive. Now, the final thing that remains to be discussed is how do we compute this reflected ray geometrically? So if I have a surface, if this is my primary ray, and if this is the normal of the surface, what will be this reflected ray? Okay, this reflected ray, finding this geometrically is the final thing that we need to do. The formula is already on the slide, but let's look at the derivation of that formula. If we call this angle theta, the perfect reflection ray should have the same angle of the angle of incidence should be equal to the angle of reflection. So this is what we should have. If you consider this primary ray also towards this direction, because we have, if you remember, these vectors here, while we were computing it with for the specular component, this primary ray, we use this vector as the two viewer, or the view vector is something from this point towards the eye point. If this is my eye, my vector is in this direction. Okay, this is my primary. The ray is actually in this direction, but at this point when I'm computing the color components, when I have this v vector, l vector, n vector, if you think about these vectors, this L vector was the vector which states that it's the to light vector. Okay, so this -1 is the L vector and it's this direction. Normal is also from the point outside the surface. So this is also, and our shadow ray, if I have a shadow ray, also is from this point X towards the, again, the light source. So the view vector is also from this point X to the eye. Okay, so let's call this vector view vector. Now, knowing the view vector and the n vector, the normal vector, how can we compute the reflection vector? Let's call it R. All these vectors, v, l, n, s, r, they are vectors and they are from point X outside towards outside the surface. So from it originates from point X, and all of them we want them to be normalized. We want their sizes to be 1.0, maybe except the shadow ray. We don't want to normalize the shadow ray, maybe because we may want to do the check with between t is equal to 0 and 1. If you want to do that, we don't want to normalize the shadow ray. But this light ray, which is the same direction as the shadow ray, we want it to be normalized because with normal vectors, we can just use their dot products directly without dividing by their length to get the cos alpha or cos theta. Okay, so in order to do that, we normalize them. Now, if our goal will be to compute, given v and n, v is this and n is this, compute r. What is r? if v and n is given. So in order to do that, if you look at the situation around x, how v and r are looking, we see that v plus r, if I add v plus r, I would get a vector in the same direction as the normal vector. So if you look at this, for example, with respect to this plane, with respect to this normal vector, they have a certain component. They're the direction, the component which is orthogonal to the direction of this plane. The components of these vectors are in the same direction. So when we add these two vectors, if you do v plus r, whatever component they have towards in the normal direction, they will be added to each other. All right, and if you look at their direction parallel to the plane, they are exactly in opposite directions, and they cancel each other out. So after the addition, I will have some vector with which is going to be actually orthogonal to this plane in the same as normal direction, but with potentially length which is equal to the projection of these vectors on this normal vector. So it's going to be something like this, n times some constant. So if I add v and r, I will get a vector in the same direction as n, potentially with a different length than n, because I will be adding. So what is the projection of v on this normal vector? It's going to be actually v cos theta, and this is going to be r cos theta. These are going to be the length. Its length is going to be this, whatever the length of v, whatever. And since these were unit vectors, since this is 1 and this is 1, okay, so what happens is that if you actually, I can know that when I add these two vectors v and r, the summation, its length will be equal to 2 cos theta. So it's going to be equal to this. V plus r is going to be a vector in the direction of n with length 2 cos theta. Okay, so this is, and if our goal was to find r, if we put this v to the right hand side, okay, we get our formula. R is equal to n times 2 cos theta minus v, and this cos theta, we can simply find cos theta by the dot product of v and l, right? So cos theta is equal to v dot m product n, which is also known. Since these are unit vectors, it gives me cos theta directly. So what I do is I multiply 2 with the dot. I compute the dot product between the v vector and the normal vector. That gives me cos theta. I multiply it with 2, and I multiply the result with n. If I subtract the v vector from it, I get the reflection vector. And this should be the exact same formula that is written here. Okay, yeah, as you can see, it's the same formula. 2 cos theta, this is my normal vector, this is my v vector towards the camera. I have it minus v as in I have here in GIMP. It's minus v. So the formula is driven by using this. Okay, I hope this is clear. And this concludes our discussion on ray tracing shading, and it completes everything you need to know for the assignment. For the assignment, you will not be needing anything else. For intersection tests in the assignment, for triangles, you can use either the barycentric coordinate one or the simple idea, but I told you that simple idea which uses intersection of ray with the plane is a little bit slower, but you can make things faster by pre-computing certain things, like if you remember the plane equation for each triangle, for example, the plane equations may be computed beforehand for each triangle in your scene, so that you don't need to recompute the plane every time you do the intersection test for different rays. Yeah, and the final image with the reflection edit is going to look like this. So this reflection is going to be edited just as a fourth component to our color computation, and this L is computed by multiplying the reflection coefficient of the material with the incoming ray color. And here are some example images we have went over last time, so I'm skipping those. All right, any questions about this part before I move on to a new topic, which we are not responsible in the assignment, but you may use some of the ideas in that new topic if you want to get this bonus part of your of the assignment. In order to be able to get the bonus part, if I'm not mistaken, the fastest, some of the fastest ray tracers are going to receive some bonus points. And in order to be able to get these points, I think I'm sure some of the groups will implement some data structures to speed up the intersection test. And for that, you will need to learn like the bounding volume hierarchy we are going to cover in the next part of the lecture. All right, so I'm going to then move over to the new set of slides. There are no questions, which is data structures for graphics. And here we are going to see how we can represent our triangular meshes in a good data structure to allow for efficient query of faces, triangles associated with that. As faces, we will have triangles, or edges associated with those triangles, getting to the neighbors of a given face easily, finding the incident faces of a vertex easily. So we need, in order to make these queries efficiently, we need a nice data structure that allows us to do that. So we are going to, in the first part, we are going to talk about these triangular meshes, the index face structure, which is very similar to the format we are using for our assignment. Our XML format is actually an indexed face structure. We are going to talk about those. And at the second part of this data structures, we are going to talk about how we can index our scene for more efficient computation of ray intersections. So it's composed of two parts basically. How to represent the objects, the entire objects, the triangular meshes as an efficient data structure that allows for queries on the object itself. The other is index structures for our entire scene to make ray intersection tests more efficiently. All right, so this is the next part we're going to cover. All right, so in this first part, we learned the ray tracing algorithm basics. Some of our objects are mathematical objects like spheres, with just the center of the sphere and its radius is given to us. So arbitrary objects are triangular meshes. Yeah, as I said, these slides are organized in two parts: how to represent triangular meshes efficiently, and how to organize them efficiently by using index structures for our three-dimensional scenes. So triangular meshes are really common in the graphics world, and many computer graphics cards, I mean graphics cards, the graphic acceleration cards, actually the benchmarks are based on how many triangles they can render in a second, or how many frames per second they can achieve, for example, in a scene which has 10 million triangles, 20 million triangles, things like that. So the number of triangles and how many triangles you can render at a second is something that is used to measure the efficiency, measure the performance of a graphics card. So triangular meshes are really popular. Quadrilateral meshes are also popular. Instead of reusing triangles as primitive objects, you may also use quads. But yeah, there may be some degeneracies at quads if you're not careful. So triangles are in that regard better. There are many modeling tools which actually check a given model in terms of these degeneracies. For example, are there edges which are not part of any face? Or for example, are there any holes in your object? Some vertices, are there dangling vertices? So they're given an object representation with the vertices, edges, and faces, we can actually do some consistency checks whether this object is a nice close triangular mesh. Especially these errors may happen if you get your model from a 3D scanner. 3D scanners give you point clouds, and these point clouds can be triangulated. There are algorithms, for example, like Delanoë triangulation, which allow you to generate these triangles automatically by combining nearby points into triangles if you are given a point cloud. So that's an interesting, different problem. If some object's representation is given to you as just a point cloud, how can you turn it into a triangular mesh in such a way that the triangles that I'm going to put are going to be fat triangles? I don't want very narrow triangles. I don't want to connect the points that are far away from each other, which will result in thin triangles. So actually there are algorithms to do that, like Delanoë triangulation is one of the methods that give you a nice triangulation of point clouds. And I think this is detailed. These algorithms are detailed in Yusuf Hoca's course, digital geometry processing. This should be the topic of digital geometry processing. Okay, anyway, too much detail, but what I want to say from here is that triangular meshes are really popular, and even curved objects, we can model them with lots of triangles. If you have enough number of triangles, you would be able to represent an arbitrary amount of detail by increasing the number of triangles. And in spheres, for example, or in, if you look at the circle, if you can increase this piecewise, sometimes this is called piecewise linear approximation of the surface, because we are approximating a given continuous smooth surface by piecewise lines in 2D, and in 3D we are going to be approximating the surface by triangles or planes, okay, by polygons. So a polygonal approximation of a smooth surface is also a piecewise linear approximation, because polygons are linear objects. They're the extension of lines onto 3D. So if we have more polygons to represent a sphere like this, the sphere is going to look more like a sphere, and we will not be able to distinguish it from a real smooth sphere. Okay, so that's one idea, to increase the number of polygons to represent that. Our triangle objects, the term mesh is used to understand that triangles are connected together to form a surface. And the surfaces that we are going to discuss here, they actually are called two-dimensional manifolds. We will be interested in two-dimensional manifold. A manifold is something in which, if you look at the local neighborhood of a point, it resembles a 2D Euclidean space. I mean, although this like sphere is a three-dimensional object with some curvature on it, if you look at close enough at a point, its surrounding resembles very much like a plane. So if the property of the Euclidean, so mathematically, in mathematics, these manifolds are discussed a lot. So there are very interesting shapes in topology. For example, there are certain shapes which are not possible three-dimensionally, but that's also a two-dimensional manifold. But you can just think about these two-dimensional manifold as surfaces, three-dimensional surfaces in which the surface could be parameterized by two things. In other words, if you're on a position on this 2D surface, you can it resembles a plane, and you can parameterize this by using two variables, which means that it's like actually it's a two-dimensional entity. Yes, if this was a sphere with the longitude and latitude, you can uniquely identify any point here. So it's this is what a manifold is. So here are some properties of manifolds. each edge will be shared by at most 2 faces. There will not be 3 faces sticking out from an edge. All right, so each face, each edge will be adjacent to, it will be incident to. So also there are these 2 terms, you should know them in their correct meaning, being incident and adjacent. Okay, so adjacency is between same type of objects. For example, this vertex is adjacent to this vertex. Vertices could be adjacent to each other. Edges could be adjacent to each other. So this edge is also adjacent to this. So if they are 2 same type objects, if they're neighbors, we use the term adjacency. Okay. On the other hand, incidency is between 2 different types of objects. For example, a vertex may be incident on this edge, which means that vertex is one of the endpoints of this edge. Or a face may be an edge may be incident on a face in that case. So this means that this edge is part of this face. Okay, so incidency is about different type of objects. When we talk about different type of objects, we use the term incident, and adjacent is between the same type of object. So these 2 vertices are adjacent. So in other words, an edge is shared by at most 2 faces means that an edge, I could have said the same thing, an edge is incident on at most 2 faces. Okay, and also faces containing a vertex form a closed or open fan. For example, if you look at this again, faces containing a vertex, again we can say faces incident on a vertex. If you look at this vertex, the faces around it form a closed fan. Starting with this face, I can say this face, this face, this. I can actually follow through all the faces around this vertex, and they are forming a closed loop around the vertex. I will come to the next face again. Or sometimes it will be, I will start from here, come here, here, and the next face, there is no such thing. So if it's a vertex that is at the boundary, they may not form a closed loop around the vertex, which we call in such a case as an open fan. So these are just think about manifolds or surfaces as three-dimensional surfaces in which it's a 2-dimensional manifold because the surface is just like the surface of a sphere. Okay, any arbitrary objects. For example, if you look at this one, this is like also, it's not a sphere, it's a dolphin. We can clearly see, but it's a manifold because it's a closed form 2-dimensional manifold in a 3-dimensional world. If you look at closely at a certain point, the space around it resembles a 2-dimensional plane wherever you are. So you can parameterize the triangles on this dolphin by 2 values. And there are no holes in it. If there are holes in it, that will be a different thing. But we can still have objects like toruses that have holes in them, but they are still like 2-dimensional manifolds. All right, I think it's a good point now. To understand what are not manifolds, it's good to look at some counterexamples. If you look at this shape, an edge is incident on 3 faces. If you look at this edge here, right under the mouse pointer, it's incident on this face, and this face, 3 faces. So this is not a manifold. Also, if you follow the faces around this vertex, they do not form fan. One of the faces are sticking out like this. This is also not a manifold. As you can see, it's not possible to have. If you look at the space around this vertex, it doesn't resemble a 2-dimensional plane. There is something sticking out. So therefore, this is not a 2-dimensional manifold. These may be still valid 3-dimensional objects you may have in your, but you would represent them maybe as 2 separate parts if your algorithm really depends on manifolds. You may ask, actually, in our ray tracing algorithm, does it really matter that they're manifolds? Actually, no. If you just have your triangles listed separately, our ray tracing algorithm does not care about whether the underlying surfaces are manifolds or not, okay? Because we just treat the ray tracing algorithm can render these non-manifolds perfectly fine. But these manifolds will be important for if we want to have some other surface properties in an object, or if you have a data structure which assumes the underlying object is a manifold, then this property will be important. Okay, now let's have a 10-minute break. So it's break time. I will continue with triangular meshes and how we can represent them with certain data structures. And I may even talk about, for example, if this was a two-dimensional triangular mesh like this, there are in computational geometry, there's a data structure called doubly connected edge list, which may help you to make queries like find all of the faces that are incident on a given vertex quickly, or given a face, find the neighboring faces. So it's a data structure that allows you these things. I will also mention about that. It can even be used in three-dimensional structures too, but on the slides it's not detailed. So this doubly connected edge list is something I teach in computational geometry, but I think it's also relevant to this idea of data structures we have here. So I will briefly mention about this as well. All right, so let's have a 10-minute break now, and after the break we will continue with the data structures. Okay, I will stop recording.